Good afternoon, everyone. We're going to give everyone a chance to join. So I'll wait for another 30 seconds or so, and then we can get started. Okay, let's get started. Today's topic is rooftop units fundamentals. Last week we talked about VRF systems, and this is just a part of our overall webinar series where we're going through an individual piece of equipment and trying to help everyone understand when is best to use it, how does the piece of equipment work, and what projects are best with that type of equipment. So today, topic 3 is about rooftop unit fundamentals. First thing I want to talk about, all of these recordings are available on our website, ceshv.com. If you hit the education tab, there's a drop down. If you hit the webinar recordings, there's a list of the 2 that we've already done, which are the fundamentals, which was week 1. Last week was VRF, that's there. And then after this recording is done today, we'll upload the rooftop unit fundamentals one. So, in case you missed the live webinar, you can always go back and check out the recordings on our website. If you've been to some of these sessions, you already heard about who I am, but if you're new, my name is Jack Corcoran. I work at Caton Energy Solutions. We are a manufacturer's representative firm in New York City, Long Island, New Jersey area. We help engineers and contractors procure equipment, size the equipment for the project, get cut sheets and all that. Really, we just help out other members of the project team to get the equipment selections done correctly. A little bit about myself. I went to University of Notre Dame, go Irish. I got my mechanical engineering degree, and I went on to work as a design engineer at AMA Group, which is now CMTA in New York City. And with all that experience, I was able to get my PE, my professional engineering license, and I'm now licensed in a few states around the country. So where does this session sit in the series? Today, we're going to talk about rooftop unit fundamentals, right? Next week is a little different. We shuffled things around to work out better with what people were looking for. So, this week is rooftop fundamentals. Next week, we're going to talk about DOAS units, ventilation and outside air requirements. And the following week, we're going to talk about gas detection fundamentals, right? And how that closely relates to our outside air requirements. And with all of our sessions, I have a promise to all of you, right? And this is the same promise I'll make across all of our presentations in this series. The first thing that we're going to cover today is how do you identify a rooftop unit, and what system loops does it use? The second thing is understanding each of the components. There are many components in a rooftop unit, which ones are key and which ones are part of the overall system, so you can recognize what's in it. Third is listing the advantages and disadvantages of rooftop units. And lastly, we're going to determine when a rooftop unit should be used, right? We'll go through a couple example projects at the end of the presentation. So back to this diagram, this is going to be, a thread throughout all of our presentations. How are we moving heat, right? Every piece of equipment, every system that we work with in the HVAC industry is going to be able to tie back into, one or multiple of these loops. They're named across the bottom, right? You have your, and left to right, air side loop, you have your chilled water loop, refrigerant loop, heat rejection loop, and your controls loop. So today's topic is rooftop units. Which ones or which one of these loops is being utilized? These three, right? We have our air side loop, our refrigeration loop, and our controls loop. If anyone was on last week, you'll remember these are actually the same exact loops that we use in the VRF systems, right? But if anyone knows anything about rooftops and VRF, they look very, very different. So that's why today we're going to dive a little bit deeper in to see actually where the differences are, and what drives the advantages and disadvantages of each configuration. So here on the left side, we have packaged rooftop units, right? The idea behind these rooftops is that they're packaged and every single component ships in one factory assembled cabinet, right? You got your heating and cooling coils, your fan, your compressor, filters, dampers, controls, everything is located in one central location and it's all on the roof, right? On the left image, you can see, there's a lot going on in that package cabinet. Um, you know, it's complicated. It looks complicated from this section view, but if you just look at it, it's a box sitting on your roof, with ducts coming out the bottom of it. So essentially, this is where our two loops, the refrigeration loop and our air side loop, intertwine, right? And we'll have the refrigeration loop entirely located on the roof in the cabinet, but the air side loop actually extends into the building, and the ductwork is what allows that air to travel from the occupied space into the rooftop unit on the roof. So essentially, the whole system's on the roof, and you got ductwork extending down into each zone. These are just, another way to show it. The architecture of the ductwork, can be important and has its advantages and disadvantages. So here at a high level, right, you can see on the right side, we have one unit and it's distributing ductwork throughout to multiple rooms in multiple zones. Uh, this is a very, very strong application and, used very, very commonly throughout the industry. Each one of these zones is going to be able to be controlled independently, right? It's a VAV system. So you have VAV boxes that'll, open and close the damper to allow more or less air, and that means you have multiple thermostats, multiple zones, and you can have different diversities here, right? But on the left side, you see there's only one thermostat, and it looks like this is only distributing into one big room, right? You're only going to be able to dump a certain amount of air into the space with this constant volume system on the left. Now, a key distinction here, right? Last week, again, we talked about VRF systems. VRF systems send refrigerant throughout the building to each zone to control the temperature, whereas rooftop units send air via ductwork throughout the building. So those are the two key distinctions here. We use the same three loops, but instead of sending the refrigerant through piping, we're sending air through ductwork throughout the building, right? We'll dive into that a little bit more later on. Yeah, and so this is just another way of looking at it, right? We're still using our system loops that we had before. I drew a box around the refrigeration cycle, the refrigeration loop, and then part of the air side loop, right? Because that's all packaged within that box on the roof. And then, outside the box on the left side, we have the supply air ductwork and the return air ductwork going back and forth between your space and your rooftop. Nothing changes here, right? Our heat is moving from the left side all the way out to the right side. The occupied space is generating our heat, right? And we're going to have to remove that heat from the air side loop into the refrigeration loop and then into the ambient air, right? And so we're not changing anything fundamentally here. It's just a matter of where each component fits in the configuration of the system. So now we know a little bit what rooftops might look like, right? We use our two loops, air side refrigeration and controls to make sure everything runs smoothly. It's all packaged on the roof. And, while it uses the same loops as VRF, we have a different architecture here. So let's dive into the components and why rooftop units work the way they do. So the easiest way to examine a rooftop unit is to follow the air through it, right? If you can imagine this crude looking box is your rooftop unit, you just have 4 sections in this rooftop unit, right? Our air is going to flow in the left side. Our outside air and return air is going to mix. It'll pass it passes in via the dampers or the economizer. Then it goes over your filters, over your cooling coil, and then your fan is what pushes it back out into the building. So, you know, you can follow the air left to right, and in any rooftop unit, if you looked inside of it, you could find these 4 components, maybe some extras, maybe not all 4 of these, but you're going to have different sections. Follow the air through the unit, and you'll be able to identify which components are being used. So the first component, our dampers and our economizers, right? So this is all about mass balance, right? Our airflow balance. So you have a fixed amount of supply air that's going out of our unit. So you need to have air coming into the unit in order for that to work. So if you look at our mass balance equation here, our outside air plus the return air, those are the 2 sources of air coming into the unit, and that's going to equal the air going out, which is the supply air and the relief or exhaust air, right? And so in order to have a equally pressurized building, that equation has to be true. The air coming in has to equal the air coming out. But how does that get set? We all know that we need to have a certain amount of outside air per code, right? So our outside air damper on the left side of this image opens and closes to let in the required outside air, right? It's going to let in 20% of your air is going to come as outside air, and the other 80% is going to be let in as return air. There has to be some sort of sequence of dampers that open and close or are set at a fixed level that'll allow that outside air come in at 20% and your return air to come back to the unit at 80%. But where does the other 20% of the return air go? It has to be spilled out, right? And that's all part of the mass balance equation. That is spilled out of the building as relief or exhaust air, and the exhaust or relief damper is what allows that to be balanced to the correct CFM. Now that's all great, but we have energy requirements, right? So if you're just dumping that return air outside, potentially you're losing energy, and if you're bringing in all this outside air that's really, really hot or really, really cold, you could be spending a lot of energy trying to temper that back into the room temperature. In order to make this a smarter system, more energy efficient, right, we have economizers. And so all that is an actuator, a sensor, and a sequence of operations that basically allows the outside air quantity to modulate. You don't have a fixed volume of outside air anymore. When the outside air conditions are correct, right, and it's 50 degrees outside or 55 degrees out, that is the perfect temperature to bring it into our building, right? So instead of having 20% outside air come in, we're going to open up that outside air damper to 100%, right? You might as well take advantage of all that free cooling. 55-degree air, you don't have to spend any energy to cool it back down because it's already at the temperature you need it. Outside air damper opens, return air damper closes, and all of that return air goes out as relief air. And you save energy, right? You're not using any energy on your cooling coil or your heating coil because it's free energy, right? And this is required by code. Our energy codes in New York City and New York State and New Jersey State, you have to have an economizer if you are over a certain amount of CFM. It's just a really, really great way, an easy way in rooftop units to get, a lot of energy savings. So following our airflow through the unit, the next thing it'll hit is your filters, right? These are very important. Not only do these act as the first line of defense for your air quality of the occupied space, it also protects your equipment, right? So if you have high efficiency filters, you're going to have very, very high quality indoor air, right? There's not going to be a lot of particulates or bacteria. All of that is going to be stopped at the filter, and then you switch them out and change them every few months in order to, you know, that bacteria, that dirt, that debris never actually gets into the space. Um, so it's clean air in the space for the indoor air quality, and also you don't get any dirt or debris that gets on your cooling coils or gunks up your fan. All of that affects the efficiency of those pieces of equipment. And if we can stick those filters in there, they kind of do two things at once: makes your indoor air high quality and clean, and it also protects your equipment in the packaged unit. So we use, typically we use MERV filters, right? The minimum efficiency reporting value, 1 through 16. MERV 8, MERV 13 are pretty common as a pre-filter and final filter. You set them up in a pre and final filter often because, you can imagine that the higher the MERV, the cleaner the air, right? And so the more that you're going to capture on your filter, and maybe the more often you're going to have to replace it. So, if you can capture a lot of the big stuff with a low MERV filter, like a MERV 8, then you can have the MERV 13 downstream. You don't have to change out your high MERV filter, which could be much, much more expensive than your MERV 8. Maybe you may change your MERV 13 twice a year, and you change your MERV 8s 4 times a year, so you don't have to, continuously change your high MERV filters and spend a lot of money. That's just a common configuration, saves you money, and also gets you the high quality clean air you need inside. But the reason you switch them out at all, I mean, if you wanted to get rid of all that dirt and debris, right, to have a clean unit. But the more dirt and debris that gets caught, the higher the pressure drop, right? Your fan is going to be using more energy. You're going to be working twice as hard if you have all that gunked up dirt, debris in your filters. So you want to replace them pretty often so you don't have that high pressure drop through the filters. Also, just inherently, higher MERV is going to have a higher pressure drop. So it is a balancing act, right? Why you could just get a MERV 16, MERV 13 filter every time, right? But have the super clean and high quality indoor air, but you have a higher pressure drop and you're using a lot of energy, right? So it does become a balancing act, and it is all about what your project requirements are. And continuing down the line in our rooftop unit, right, we're going to hit our cooling coil next, right? So this is our DX, or direct expansion cooling coil. That is a little hint back at our refrigeration cycle, right? This is where the two loops meet. We're going to have our refrigeration loop is going to, our cold refrigerant is going to be in the coil, and our hot air is going to be passing over it. So, when our return and our outside air mix, they're going to pass over the filters. They're going to then pass over this coil, right? As hot, wet air passes over a cold coil, you're going to drop your air temperature, right? That's our sensible cooling. And we're going to condense the moisture out of the air, right? That's our latent cooling. This coil is going to allow us to achieve the temperature and the humidities that we want in our space, just by nature of having, the intersection of our two loops here. Our coil temperature is low, so we're going to be lower than the dew point, and we're going to be lower than the air temperature, the dry bulb temp. So you get a both sensible and latent cooling out of this portion of the rooftop unit, which is a very powerful tool. Right? We always want to have the correct temperature and the correct humidity in our spaces, and this coil allows us to do that. So you can actually see at this coil, heat leaves the air in two places. As we said, it's sensible heat, right? Our air gets colder, right? So that heat from the air goes directly into the refrigerant. The refrigerant changes phases, as we talked about last week. The refrigerant changes from liquid into vapor, and so that goes out and rejects the atmosphere. However, we're also going to get rid of heat in our condensate, right? So all the sensible heat goes into the refrigerant, but just because we're colder than the dew point of the air, we're going to actually condense the heat and the moisture out of the air with condensate, and that has to drain out of the unit to like a floor sink or to a sink or a floor drain. And the next section is our heating section, right? We followed our air through our outside air dampers, our return dampers, went through the filters, went through our cooling coil. If we're in heating season, that cooling coil is off, right? And we're going to have this heating section on. It's the same deal, right? We're going to have our outside air and our return air, which is cold this time, pass over the coil or the manifold or any form of heat, right? So we're providing our heat. These icons say it all, right? We can use gas heating, we can use electric heating, we can use heat pump heating, or hot water or steam heating. Um, Oftentimes, our packaged rooftop units are defined by the type of heat they use. You'll hear terms like packaged rooftop unit with direct fired gas heating or packaged rooftop unit with heat pump heating. You know, it depends, or like electric heating, electric cooling. So you'll hear that the heating section often defines the type of rooftop unit that you use. Um, and because it's so flexible, you have different options. Our gas heating is usually our propane or our natural gas. Uh, Electrical heating just uses a resistance heat coil, right? It's just one-to-one electric heat, or we can use heat pump heating, running our refrigeration cycle in reverse. In that case, you actually don't have a different heating coil. You would have the same DX coil would just operate in reverse. Or you can have hot water or steam heating. These two are not part of a packaged rooftop, but it is worth noting because those are the other two ways you can get, heating in your unit. Those two require a separate system, right? You can have a boiler, or Con Ed steam, or somehow you need to get hot water and steam, and that's not part of the packaged rooftop. That would be a separate system. If the building already has that available, you just add in a hot water coil to the packaged rooftop and call it a day. And the next section you could have is a reheat coil, right? So in cooling mode, we mentioned that we get a lot of latent cooling just by having our coil temperature lower than the dew point. Many times you're going to have situations where the outside air volume is super high, right? And in the middle of the summer in New York, we all know it gets very, very humid. You're going to have to overcool your air, right? Or have your coil temperature be lower because the dew point of the air, you want to extract a lot of moisture. So you need to have a low coil temperature, right? But by having a low coil temperature, you're also going to overcool the temperature of the air, right? So you're going to be coming off at now 52 degrees Fahrenheit instead of maybe 55. And that's too cold to send throughout the space. You're gonna get condensation on ducts. You're gonna get maybe condensation on surfaces in the room. But you can have a reheat coil section, right? We overcool our air, wring out the moisture, and then we reheat it back up to whatever temperature we need, right? So if the space is cold but damp, we can reheat it back. We can overcool to get rid of the moisture, and then we can reheat it back up with our reheat coil section in order to get our 70-degree room air temperature that's dry into the room, not a moist 70 degrees. So as we said, right, we have sensible cooling, latent cooling, and then we have sensible reheating. The humidity remains low, but the temperature increases to what we need for the space. And we have a couple different ways we can achieve the reheat. The most economical way to do it in a packaged rooftop unit is with hot gas reheat. This is great because it just uses the waste heat in the refrigeration cycle it just has another coil upstream. Our compressor is just going to send the hot gas to a reheat coil, and that allows us to get a little bit of sensible heating without having an entirely separate heating section, right? We could use gas reheat, or we could use electric reheat, or hot water or steam, but as we said, if we don't have to use that energy, we already have it from our DX coil for overcooling the air. Why not just run a little bit of hot gas back to our a little bit downstream, and that way we save energy, and we also get the reheat and dehumidification that we need. So this is a very powerful tool when you have high latent loads or high humidity that you want to get rid of. And the last thing that your airflow sees before it leaves the unit is the fan, right? Your fan is what the supply fan pulls your air through the unit and then pushes it out into the space, right? So your fans are very important. They're going to dictate the amount of CFM that you have available. Larger fan, more CFM. It's also going to dictate the static pressure, right? More horsepower, more static, more CFM. The bigger the fan, the bigger the blades, the more you can get out of it, right? And so the supply fan is a very important piece of your rooftop unit, and it is driving your airside loop throughout the rest of the building. You can have a couple different types: direct drive, belt drive, and the way you control the fan on the supply side can be constant volume, or it can be variable air volume, depending on how you want to control the temperature in the space. We'll talk about that a little bit later on. But that's your supply side, right? All your supply air needs to be pushed out through the air side loop somehow, and that's dictated by your supply fan. You can also have exhaust or relief fans. Oftentimes, this is, in smaller systems, not required. Your supply fan has enough static pressure to pull your return air back into the building, and your dampers just modulate open and close to allow the CFM. But sometimes you want to keep those airstreams separate. When you have energy recovery heat wheels, you need to have a separate fan so that because if the airstreams don't really touch each other, you're going to need to have two fans. You need to have a way to push the supply air and pull the exhaust air out of the building. Another situation that you would use an exhaust or relief fan is if you have large volumes of exhaust or relief air and the dampers can't handle it as precisely. You can imagine that just opening and closing dampers is not going to dial in your CFM very, very precisely. So if you have a huge volume of it, you have big dampers, it's much easier to dial in a CFM at fans than it is with dampers. So if you have large CFMs, that's another reason you can use them. And lastly, another reason would be static pressure. So if you have a fully ducted return, that static pressure can quickly add up, and maybe the supply fan can't handle the static pressure, right? So you could have low CFM, high static pressure. You don't want to have this massive fan for 800 or 1,000 CFM. You maybe just separate it out into two fans and call it a day. Right, so we just followed the air through the unit, right? We followed it through these four portions, and we actually talked about a heating coil section, and we also talked about the reheat section. But we can also add in our refrigeration loop, right? So if we want to talk about where it actually overlaps, we can see with this color diagram, right? Our green components are part of our refrigeration loop, and our yellow colored sections are our airside loop. So our DX coil is where it all meets. We talked about that a little bit earlier. That's where we absorb the heat from the airside loop into the refrigeration loop. And then that's what our little Q squiggly arrow is here. And then it gets rejected into the atmosphere at our condenser. And that's where the other Q squiggly arrow is. So all these sections make up our rooftop unit. The airside loop, you follow the air through the system, and the refrigeration loop, you just follow the refrigerant through the system. It's the exact same refrigeration loop we talked about last week in our VRF fundamentals presentation, right? All we're trying to do is achieve a cold coil where the air flows over it and a hot condenser so we can reject heat down the temperature gradient, right? So heat naturally flows from hot to cold. We want our hot air to transfer to our cold evaporator. And then, we want our hot condenser to transfer heat to our hot ambient at 95-degree ambient. 115 degrees condenser is going to do that trick. So, but really, what are we doing here? We're manipulating the pressure in order to get those temperatures. Remember, we have to add in work. This is where all of our energy consumption is at our compressor, right? We are pressurizing our refrigerant. we are making it high temp, high pressure on the right side, and we are then using our expansion valve to reduce that pressure and make it low temperature refrigerant to send back to our indoor DX cooling coil. So this we talked about last week in VRF fundamentals a little bit more if you want to go back to that presentation. But essentially, we're making a hot and a low temperature side, and we're just manipulating pressures to do that. So our four components, our compressor, condenser and condenser fans, expansion valve, and evaporator, right? We follow our loop. We go from hot to cold and high to low pressure. These are two rooftop units you can see on the left side. Really, when you're looking at them, you can just tell that the one on the bottom is actually higher capacity because it has more condenser fans. That's what those fans on the top are. They actually reject the heat to the atmosphere. So you can imagine bigger condenser coil, bigger condenser fans, or more condenser fans, bigger capacity. And the top one only has one fan and a smaller condenser coil, so that's a smaller capacity unit. Rooftops look all sorts of shapes and sizes, but these are just two of them. But they take advantage of the refrigeration loop, just like our VRF system. Now, how do these control capacity, right? We talked about our VAV systems, our variable air volume, and our constant volume systems. These are the two main control paths that we use in our rooftop units. You can imagine that, in order to control capacity, we can either vary the airflow, right? If we send more cold air to a space or less cold air to a space, we're going to change the temperature of it. Or we just send hotter air or colder air to the space in order to change the temperature. And that's what these two systems are. Right on the left side, we showed earlier these two images at the bottom. The left side, you have one zone. We're going to dump constant volume of air. The CFM does not change, but we're going to vary the temperature of the supply air in order to meet our zone space temperature, right? There's only one thermostat. We're going to stage our compressors, right? Our compressors, like in VRF, slowed down in order to meet the load. In rooftop units, compressors can be staged, right? So if you have, your high, medium, low settings, I guess is the easiest way to describe it. Your compressors won't be able to dial in 0 to 100%. Maybe you could just dial it, to high, medium, low, and off. So you'll stage the compressor from high to low and then to off, depending on how satisfied the space temperature is. And that staging of the compressors is going to change the temperature of our air. Less compressors on means higher temperature air until it's off, and then it's just recirculating. The drawbacks of this is that I will say many modern rooftop units can use variable speed compressors that can modulate just like VRF, and those are very powerful, but they add to the cost, and maybe you don't need it. So the simple rooftop configuration, constant volume with stage compressors, and some trade-offs that you can imagine that come with this are that you can only step the capacity, right? What if you wanted somewhere in between high and low heat or high and low cooling? You're either going to be overcooling it or undercooling it, depending on if you pick the high or the low mode to be in. You're going to overcool, turn it off, then it'll drift back up, turn it on, overcool, turn it off. So that maybe is not what you want in your space. But that's one way to do it. It's very simple. Another way, another trade-off actually is that this is best for single zones, right? If you had different areas of the floor that needed a different amount of cooling or heating, this is only going to be able to send one temperature throughout the whole system. So every zone that it sends it to is going to be the same temperature, right? You can't have one room be hot and one room be cold. You're going to be stuck with what you got. So that's why it's better for large open areas, not a zone by zone control. And we mentioned last week and a little bit earlier, the latent cooling gets achieved with low coil temperatures. When we stage our compressors down, our coil temperature rises, and there's a risk for that coil temperature to go above our dew point, and we won't get any latent cooling. You could have a freezing cold, humid, wet space, and that's not what you want. Um, so, I mean, you could always add in reheat and stuff, but that is a risk if you don't have that portion of the rooftop unit. And then on the right side, our variable air volume, our VAV system. I said this is a powerful tool. This is used a lot in our office spaces and in New York City. We're going to vary the airflow and keep the temperature of the air constant, right? So if a zone is reaches the correct temperature, we don't want to send any more cooling. We lower the amount of airflow that's going to the zone, and less cold air will allow the space to maintain or get a little bit warmer. And as soon as it gets too warm, then we're going to open up our damper, allow more airflow in, and that'll cool down our space, right? So this is very powerful. You can have dampers in individual zones, right? Our VAVs are going to be for a group of offices, an individual office. Every zone is going to be able to modulate the temperature in real time. You're going to be able to get multiple zones, all with diverse loads, satisfied with this system. Of course, the trade-off that we're going to have here is you can't modulate it down to zero. There's a minimum airflow per code to every zone based on the number of people and the square footage. So if you have a high outside air requirement in each zone, your minimum airflow, right? You're going to only be able to turn down to the minimum. It might be 50 to 70% of your zone airflow is going to be required. So you're going to be overcooling that space pretty often. If you don't have another way to reheat it, or maybe you didn't separate it out from the rest of the system. So your minimum airflow based on outside air always has to be considered. Um, Without overcooling, with this variable air volume system, you can have a supply, like a little bit more of a complex control configuration where you reset the temperature similar to the constant volume system. Um, if all of your zones are satisfied, um, you can have a supply air temperature reset, and then you're sending higher temperature air, maybe not as much in variable temperatures, because you still want to be able to maintain your zone minimum airflows. But you don't have to change the air temperature as much if you're also controlling the air volume. So our components we just went over, it's all packaged on the rooftop. There's a couple different ways to control it, right? With our constant or variable air volume, but essentially you're going to follow your air through your rooftop unit, hit all of your components, and all of it gets rejected into your refrigeration loop on the roof as well. So we just covered that, and we'll go into asking the right questions, right? We're going to list out our advantages and our disadvantages of rooftop units and when we might want to use them. These are our same 10 questions we want to ask ourselves. These are our project constraints. A typical disclaimer, there's always going to be more than this that you got to think about when you're designing. But if you run through this list of 10 project constraints, you're very often going to rule out or confirm that you can use a certain piece of equipment. It's a very powerful list here that you can use on your own, walk through, ask yourself a question on a project by project basis to see, should I use rooftop units? So that's the question we're trying to answer right now. Our distance to heat rejection point, how far away is our occupied space from the roof, right? We know packaged rooftop units need to go on the roof. If we have a 50-story building in Manhattan, we're not going to be running our ductwork all the way down to the first floor. Maybe that eliminates it, and you want to use chilled water instead. Same thing with number 2, our footprint and our equipment location. I just said it, the roof is a very, very dominant constraint for rooftop units. That's where the unit is located. So even if you have a bunch of mechanical rooms in your building, you still have to have this thing on the roof. Maybe if you have mechanical rooms throughout your space, you're going to maybe look at a different solution instead of running with rooftop units. First cost, rooftop units are typically very cheap systems, right? They're simple, they're easy, they're all packaged in one unit. That's a very powerful tool for them. The number of zones and diversity. If you, as we said, your VIV system could potentially handle it, but what happens if you have, part of your building needs to be cooling and part of your building needs to be heating? You're going to run into trouble running your rooftop unit for both of those zones because it's not going to be able to do both at the same time. You can either do one or the other. Utilities, right? I mean, this is usually for the heating side of things. If we have gas, if we can't use gas and need to go electrification, rooftop units are flexible. They can handle whichever way you want to do it. A2L refrigerant limits. Everything, as we said, our refrigeration loop is contained to our roof and it's outside. This is a pretty powerful tool that we can, say is an advantage for our rooftop units because you don't have individual zones with lots of refrigerant in it. It's all packaged up at the roof. Building size and heat load. We're going to have a cap on our capacity, right? So these rooftop units can only get so big before they get pretty ridiculous. You can imagine, or I mean, it makes sense, right? We have more capacity, we have more airflow, and we have bigger ducts. So if we have, a 500 ton or 1,000 ton system, we don't want to just use one rooftop unit. That's going to be ridiculous. Our duct is going to be as big as our building. So we want to make sure that when we're picking our system type, that rooftop units have a max size before, the ductwork starts getting ridiculous, or maybe it starts taking up too much space on the roof. So that's just another thing to keep in mind. And then these last three, right? Does the owner have someone on site to maintain it? These are pretty easy. You set it and forget it, which is awesome. You don't need to have an operator on site. Redundancy and reliability. These are like popcorn. You can just stick them all over the roof, and you can have a bunch of them add up to the total tonnage. And if one goes down, you still got all the other ones up there to handle the rest of the load. That's a pretty good one if it's one large zone. But if you have one unit serving one section of the floor and there's no backup unit, then there's no redundancy there. But for reliability, these rooftop units last 20 years, if not longer, if you maintain them correctly. So these are very powerful for your mom and pop shop. Stick them on the roof. They last you forever. And, you don't have to have someone constantly watching it to make sure it doesn't break on you. And then energy efficiency. While they're not the most energy efficient on the block, there are many ways to add a module, add in a smart sequence of operations, or pick one of the higher end units that are energy efficient in order to meet any energy efficiency demand that is required in a project. They're usually pretty middle of the pack in terms of EER and IER. And here's a summary of them. Right on the left side, these are our dominant constraints for rooftop units. It's your first cost, they're cheap. Refrigerant, it's on the roof. End user capabilities, you don't need anyone looking after it. We kind of went through all these already, but these two on the bottom left were not part of our 10 questions, but they're powerful pros and advantages for these RTUs. Is this a quick project, right? And so a lot of these bigger systems are going to be more complicated on install time, right? Maybe a VRF system running all that refrigerant piping is going to take too much time, or you don't have time to run chilled water, or wait for long lead times of big condensing units or chillers. Rooftop units are typically in stock. They are shipped to site quickly, and it's just ductwork in the space, right? It's not a complicated pressurized system that needs to be tested and you're going to have an easy time installing packaged rooftop units. So if you need a quick turnaround on your project, rooftop units are a pretty good way to go. And then the last thing is multiple configurations, right? I said it's pretty flexible. You can plug and play, all your different sections depending on what your project needs. Do you need reheat? Do you not need reheat? Can you use gas or electric or heat pump heating? maybe steam or hot water. All of these, and maybe you have multiple fans, a supply or an exhaust or a relief fan. So these are very flexible depending on the type that you want to go with. And that is a powerful advantage that allows you to use it on many, many, many different projects of various types. So these are our dominant advantages and disadvantages for rooftop units. So we just went through our project constraints, and we can next go on to examples, right? This is always the last section. We want to run through what are some real world examples of when can we use a rooftop or when shouldn't we use a rooftop. So our example A is a strip mall in New Jersey. 16,000 square feet. It's a single floor strip retail center in Paramus, New Jersey. Listing out our dominant constraints, right? We have multiple tenant spaces, a single floor building with a flat roof. Our developer is driving the budget down, right? They want to maximize their profits. They're going to tell you to go with the cheapest systems. The tenants are moving in quick, so they want to be able to fit it out quickly. There's no major sources of internal heat, right? We're not going to have a huge data center here, right? Or a big pool that might cause a lot of latent heat. And then we're going to have no or minimal on-site staff. This is just a retail center, maybe mom and pop shops or small, retail stores. So we can think about, rooftop unit constraints. Let's see what we got here. Maybe this project works out for us. This is pretty much a bread and butter rooftop unit situation, right? A single floor means your roof is easy access into every space. Cheap and a fast schedule. Rooftop units are pretty much going to be the best option here. You want to stick a couple of them on the roof, right? Maybe you want to have one per tenant because maybe one tenant wants it to be hotter or cooler than the others, and you want to give each one of them their individual controls. So in this situation where we have a one-story, fast, cheap project, go with rooftop units. You're not going to go wrong. They're flexible and will be able to make it work. Our next example B is an office building in Long Island, right? We got 20,000 square foot old single tenant office building, and it's 2 stories. So dominant constraints, it's an older building, right? We don't have as much glass exterior like in these modern buildings. We're gonna have 2 floors this time and a flat roof. Since it's an office, there's gonna be a bunch of individual rooms. There's no major sources of internal heat. It's a single tenant that maybe is not this mega conglomerate corporation. They're just a small growing business. There's no one on site that handles facilities, but they do have natural gas available since it's an old existing building, and they got grandfathered in with the gas. So is this a good project for rooftop units? This definitely is a good one for rooftop units. As we said, we could stick all of our rooftop units on the roof. There are 2 floors, but running rooftop ductwork down 2 floors is relatively easy still. We're not going down 10 or 11 or 20 stories. It's just 2. So that airflow is still relatively small or relatively low, and the ductwork small and easy to stick into a shaft. And maybe in this case, since our rooftop units are flexible, we have individual zones. We use VAVs, right? Each office cluster or conference room gets its own VAV and its own thermostat, and every zone is going to be able to have its own temperature control. And we want to use gas-fired heat because they got natural gas at the site. So this is a pretty good application for packaged rooftop units. You got your gas heat, you got individual zones, VAV control, and you can stick everything on the roof, no problem. So now we have an office building in New York City that's 200,000 square feet, right? It's 10 floors, each floor is 20,000 square feet, and it's a new building. What are our dominant constraints here that were different from before? We have full glass exteriors, right? We're going to have this modern building, right? New York City's got all these full glass buildings. It's 10 stories with a flat roof. We're going to have individual zoning again per room and per tenant. Maybe there's multiple tenants on different floors. And then with this larger building, maybe the landlord has an on-site facility staff. Again, we're going to have no major sources of internal heat. There's no natural gas allowed here with local law 97 in New York City. And we want to keep those A2L refrigerant limits down, right? We don't want to deal with A2L here. Maybe that's a client-driven request, but it is one of our dominant constraints here in this project. Is this a good rooftop project? I don't think so. You could probably make it work, but I think the number one issue here is that you got 10 floors, right? You're not going to be running those rooftop units 10 stories down. You're going to be eating up very valuable real estate with shaft space where your ductwork is going to be traversing from the roof down to the floor. I mean, your architect is and your landlord is going to be telling you, we want to be able to rent out this square footage. Every square foot of rentable space has a dollar amount. You can't just be running these massive ducts up and down the building. You're going to be eating up at real estate, and the landlord doesn't want that. I mean, you don't want to do that either. You want to always be providing value for our end users and our customers, and we're smarter than that. So, as I said, that is definitely the biggest red flag here. But there are some other ones with a full glass exterior, right? You can imagine that in our shoulder seasons, you're going to have sunny sections and shady sections that are going to require heating and cooling at the same time. A rooftop unit isn't going to be able to do that. So maybe we look at VRF, right? We looked last week at that, and those are awesome. Simultaneous heating and cooling, minimal refrigerant piping shafts, right? We don't have these huge ducts traversing the building. But our last consideration point is A2L refrigerant limit. So while we have many ways to combat that with easy mitigation strategies, and if you're looking for more information on that, we're happy to help. But the landlord maybe doesn't want to do that. So chilled water or condenser water is probably it with a separate DOAS system. That way you're running water throughout your building, not refrigerant or ductwork. So example D, a large new warehouse, right? We got a 500,000 square foot new warehouse and distribution facility in upstate New York. Our dominant constraints are that we got one large open volume space. There's plenty of roof access, and it's an industrial building, so there's lots of structure and beefed up. So sticking a unit on the roof not going to require extra precautions. It's located in an industrial park. Maybe you don't care how it looks on the roof, and you can be as loud as you want. There's loose temperature control in a warehouse, right? You don't necessarily need the humidity or the temperature. You can allow it to swing a little bit more because maybe it's not people in the space, it's just storage. You can let that temperature drift down to your 55 or 60 in the winter, and you can let it get a little bit higher in the summer to like 80, 85 because you don't have people in the space, and it's not an office that requires that. Again, no natural gas allowed here in New York State, no major sources of internal heat. And the owner wants it to be simple and they want it to be cheap, which, perk up your ears, that one is always a dominant constraint for our rooftop units, right? So when you hear simple and cheap, you think rooftop units right off the bat, maybe, right? So we don't have natural gas, so we're going to need a lot of electrical heat here. And unless you want to put in even if you put in a boiler for hot water or steam, that has to be electric because there's no gas allowed, right? So you're going to have a very large electrical load here for this 500,000 square foot warehouse. That maybe is going to drive your decision to doing a different type of system. You're going to need a lot of rooftop units to cover the heat load in this space. You're going to have dozens of rooftop units sprinkled throughout the space. And as we said, we need ductwork to distribute throughout. So 500,000 square feet, you're not just dumping your air into one spot and hoping it works. You want to run this ductwork throughout the space, or have another system out there like HVLS fans that will allow that air to churn around. But rooftop units can technically work, right? You can stick as many of them on the roof as you want. They'll give you your constant volume control. You can use your heat pump or electric heating, and it'll work because you don't need that tight temperature control. Um, but maybe it's not the best decision. There are some other options out there. We'll go through that in a couple weeks. We have a different options for our large warehouses that are a much more powerful solution than rooftops, but rooftops can make it work. They're cheap, it's simple, and maybe the way you want to go. And our last example, right? So we have a large school in Newark, New Jersey. There's going to be different zones of classrooms, auditoriums, cafeterias, and gym spaces. Dominant constraints are there's diverse loads in multiple zones. This is a municipal project with lots of funding. They want reliability and long service life. They already put in a bunch of mechanical rooms in their programming planning. There's an on-site facility staff and energy efficiency goals. With all municipal buildings, they have those high energy efficiency goals. So can we use rooftop units here? Let's go the other way. Nope, I don't think this is a good solution for it. Maybe it is, but you'd have to have a lot of rooftop units, right? You'd have to have a different one per zone, um, based on having one in heating, one in cooling, one with high latent load, one low latent load. Maybe you don't want to be running ductwork all over the place, but probably the biggest key here to switching to a different system is that there are mechanical rooms available, right? If they give us mechanical rooms, let's not take up a lot of space with ductwork. Let's use water or refrigerant and run that to our mechanical rooms where we have our units. So in this situation where you have a mechanical room, lots of funding, let's go with the large chilled water plant and large air handlers in the mechanical rooms. You could make it work with rooftops. As I said, they're flexible, but maybe you're trying to fit, a square peg into a round hole. There's a better solution. And so now we're coming to the end. So our summary, right? I made that promise in the beginning. What do we want to remember about these rooftop units? We want to be able to identify the equipment, right? The whole unit sits on the roof. The airside loop and the refrigeration loop are combined, and the components that make up each one of them, you just got to follow your airflow through the unit, and your refrigeration loop is all contained in the rooftop unit too. They're plug and play, right? All of these components can be added flexibly to meet the demands of your space. Add a heating coil, add a reheat coil, take away the heating, add in an extra fan, you name it, your rooftop units can be flexible enough to handle it. So asking the right questions, we know now some of the major advantages and disadvantages, and then we work through some examples at the end. So the overall takeaway here, rooftop units are very, very flexible. They're powerful, they're cheap, and they're simple, and you want to be able to use them. They're the most powerful tool in your tool chest. You're going to reach in and grab the rooftop unit quite often because of their flexibility and because of their cheap and fast nature getting to job sites. We got 3 quick questions here. In a rooftop unit, where does the heat leave the building's air? At the supply fan housing, at the DX evaporator coil, at the outdoor air damper, or at the return air filter. Just give you guys a second. The answer is B, at the DX evaporator coil, right? That's the point where our airside loop and our refrigeration loop meet. So how do constant volume and variable air volume systems control space temperature differently, right? These are the 2 main control strategies. A, VAV varies airflow and CV varies temperature. B, the opposite, right? VAV varies temperature and CV varies airflow. C, both vary airflow and temperature, or D, both keep the airflow and temp constant. We know the answer is A, right? VAV is variable air volume airflow, and constant volume airflow varies the temperature. And our last question, which of the following is not a type of rooftop unit, right? We mentioned that the type of heating is often a way we describe these. So constant volume packaged with gas-fired heating, VAV packaged rooftop with heat pump heating, a packaged rooftop with DX coil and hot gas reheat, or a single zone packaged rooftop with chilled water reheat. Our answer is D. There's no such thing as chilled water reheat, or at least not in a packaged rooftop. So, and we know A, B, and C are types of packaged rooftops. So the answer is D. All right, we ran into the end of our hour. So thank you very much, everybody. Topic 3 was rooftop unit fundamentals. And next week, we're going to talk about DOAS, ventilation, and outside air requirements in our topic 4. So stay tuned. We're going to post the recording on our website, and you'll be able to access that later today. Thank you very much, everybody.